Now we will see that using HNF form, we can always find an integral satisfying assignment, and we also develop a condition like that we had developed for the rational numbers for satisfiability of a problem like AX equals to B. The condition looks like this. If AX equals to B is a problem and you want to find integral solutions, then the solution exists if and only if for every rational vector y, if ya is integral, then yb is an integer. How do you prove that? Let's suppose we try to prove the forward direction. There is an integral solution x naught, okay? And we'll show that this is true also. Well, it's a classic trick. You multiply y on a on both sides, so you get ya x naught, and if ya is an integer, so this whole thing is also an integer, therefore yb is an integer. So each time y a is integral, yb has to be integer if there is a solution. Let's look at the reverse direction. In the reverse direction, we have this situation that that this statement holds. So if this statement holds, how are we going to say that there is an integral solution? So first thing to observe is that because of this condition, we have ya equals to 0 implies yb equals to 0. Why that is the case? Let's suppose for some multiplication ya is equals to 0. 0 is an integer, therefore yb must be an integer. Okay, is integer, right? Let's suppose non-zero. In that case, I can scale y up and down however way I like and make y be non-integral, and then this statement will not be true anymore. Since this is for true always, then I should not be able to make y be non-integer no matter what I do, and this allows me to say that yb must be 0. So now we have yb equals to 0, therefore ax equals to b has rational solutions. This was a statement like a Farkas lemma last time in rational numbers. Now you need to show that there is an integral solution. Since the elementary operations do not affect the truth value of the both sides, elementary operation which we have seen so far, so we do that and turn this into an HNF form. So we get the B0. We assume that our matrix A looks like B0, which is in HNF form matrix. And we can easily apply B inverse on B0 and obtain BI0. Our assumption implies that B inverse B is integral. Since applying this matrix, multiplying this matrix to this matrix gives us integer numbers, therefore when you multiplying this matrix to B should also give me integral. That was assumption, right? So this is an integral. And you can see that actually if you multiply these two matrices, we obtain B. So therefore my x is, this is my solution. So we can say that ax equals to b has a solution which is integral. So let's look an example of how that works. This is a matrix which we had handled earlier, and it multiplies with 3 variables x1, x2, x3 and produces 5, 5 vector. We can see that this 5, 5 needs to be produced using a linear combination of this vector, and this vector. Okay, so and let's see how we can produce 5 and 5. We turn this into HNF form and we obtain this this column. You can see that x1 and x2 should be 5 and -2. Now what is the meaning pictorially it means? So let's suppose these 3 vectors, which we had this vector 1, vector 2, vector 3. If we plot in a 2-dimensional vector space, they look like this. Okay, these are the red vectors, are these 3 vectors, and there's a b which is 5, 5. Okay, you can see this vector, this is 5, 5, and I want to find a combination of these 3 vectors so that I can produce this vector. You can easily see that if you take the twice of this vector and this one time this, you can produce this vector. So how HNF is going to help me? If you transform into HNF form, you will find that these 2 green vectors, okay, this is 1, 0, 5, this vector and this vector also producing. If you take if you just try to work it out, you will find that if you multiply, this vector is added 5 times and then this is applied this minus 2 times, then it obtains this point.